The wow signal. You're in a folding chair. It's August of 1977. The room smells like burned coffee and cigarette smoke. You're at Ohio State University's Big Ear Radio Observatory. It's a Saturday night. Nobody expects anything. The telescope is running on automation. Printout scroll. You're not watching. Nobody is watching. And then the data captures something. It captures it silently. 72 seconds of signal. Then nothing. The telescope moves on. The universe says nothing else. The printout sits in a stack. It will sit there for 3 days, until a man named Jerry Eman picks it up. He reads the numbers. He circles 6 characters. He writes one word in red ink. That word is wow. 6 characters. That's all that stands between us and whatever sent it. 6EQJ5. Those 6 characters represent the intensity curve of a narrowband radio signal that arrived at exactly 1,420.456 megahertz, the hydrogen line, the frequency at which neutral hydrogen atoms emit radiation, the frequency that physicists on Earth had long theorized any technologically advanced civilization would use for interstellar communication, precisely because it is the most abundant and universal frequency in the cosmos. It is the loudest natural note the universe plays. Someone, or something, was broadcasting on it. Dr. Jerry Eman was a volunteer researcher working with the Search for Extraterrestrial Intelligence program at Ohio State. The Big Ear Telescope, formerly known as the Ohio State University Radio Observatory, was a Krauss-type telescope, a fixed, flat reflector roughly the size of 3 football fields, and it had been scanning the sky systematically since 1973. On the night of August the 15th, 1977, it recorded a signal that rose and fell in exactly the pattern that would be predicted from a point source fixed in space, moving through the telescope's beam as Earth rotated. Rise, peak, fall, textbook, clean. The signal originated from a direction in the constellation Sagittarius, near the Key Sagittarii star group, roughly 22,000 light-years from Earth. 22,000 years of travel time at the speed of light. Whatever sent this transmission sent it before the last ice age ended on this planet. Here's what makes this impossible. The signal was narrowband. Virtually all natural astrophysical processes produce broadband noise. They radiate across a wide spectrum simultaneously. Stars, pulsars, gas clouds, cosmic ray interactions, they're loud and wide. The wow signal was the opposite. It was a single, precise frequency. A tone, a whistle in the dark, and it registered at 30 times the intensity of the ambient background noise, which in the notations used by Eman's equipment produced a signal strength reading so unusual it had to be expressed with letters rather than numbers, because the scale simply wasn't built to accommodate it. The signal lasted 72 seconds, which is exactly how long a fixed point source could remain in the Big Ear telescope's beam given Earth's rotation. Not longer, not shorter. The telescope didn't catch it arriving. It didn't catch it leaving. It caught only the window. Eman published his analysis. The astronomical community took notice, and for the next 47 years, more than 100 separate observation campaigns targeted that precise region of sky with instruments far more sensitive than Big Ear. The Arecibo Observatory pointed there. The Allen Telescope Array pointed there. Nothing. Complete silence. The standard cosmological model says the most likely explanation is radio frequency interference, a terrestrial or near-Earth source that briefly mimicked the signature of a cosmic signal. Satellites, aircraft, military transmissions reflected signals from the ground. The scientific consensus is that the absence of any repetition is the strongest evidence against extraterrestrial origin. Natural cosmic sources tend to be periodic or continuous, and a genuine alien transmission would presumably be repeated. But the data does not cleanly support this. Radio frequency interference does not typically produce the precise rise and fall intensity curve of a point source tracking through a telescope's field of view. It does not arrive at exactly the hydrogen line. It does not vanish so completely that decades of targeted follow-up with superior equipment detect nothing at all. No interference, no natural source, no residue. Some astrophysicists suggest the signal may have been a one-time deliberate transmission, a beacon aimed not at us specifically, but sweeping the galaxy, and Earth simply happened to be in the beam for 72 seconds before it moved on. What was it tuned to say? Why the hydrogen line, and not a different frequency? Why has the source been silent for 47 years, and only 47 years? If it was interference, where is the source? If it was natural, What natural process produces a narrowband tone? The universe offered one signal, then it closed the door. And what's strange about the WOW signal is that it came from 22,000 light-years away, while the next anomaly came from something orbiting our nearest stellar neighbor, 4.2 light-years from the Sun. BLC-1, the Proxima Centauri signal. You're watching a frequency band that should be silent. It's April of 2019, and you are sitting inside the data pipeline of the Parkes Observatory in New South Wales, Australia, the same dish that received the first television signals from the Apollo 11 lunar landing. Tonight it is pointed at Proxima Centauri, the closest star to Earth beyond our own Sun, 4.24 light-years away. That distance sounds almost manageable until you sit with it. Light itself, traveling 300,000 kilometers per second, takes 4 years and nearly 3 months to cross that gap. A signal sent from there during the First World War would be arriving right about now. And something is arriving. A single, narrow tone, 982.002 megahertz. Clean, stable, drifting. You watch the drift rate. You do the math. It matches. Here's what that means. The Breakthrough Listen project, the most comprehensive and well-funded search for extraterrestrial intelligence in human history, backed by $100 million from Russian-Israeli billionaire Yuri Milner, and overseen by some of the most rigorous signal analysts on Earth, was conducting a targeted survey of Proxima Centauri during a campaign that ran from April through May of 2019. The data sat in storage for over a year. It was a PhD student at the University of California, Berkeley, Shane Smith, running routine analysis in late 2020, who first isolated what would come to be called Breakthrough Listen Candidate 1. The signal was formally reviewed by the team, and the details leaked to The Guardian and the Sydney Morning Herald in December of 2020, before any peer-reviewed paper had been published. To this day, no official publication has fully documented the detection. The data exists. The signal is real. The conversation around it has been managed carefully, in public, and less carefully in the gaps between announcements. The signal itself carries properties that make it difficult to dismiss casually. 982 megahertz sits in a region of the radio spectrum that is largely avoided by human technology. It falls outside most aviation and satellite bands. More importantly, the signal was narrowband, occupying less than 1 hertz of spectral width. Natural astrophysical phenomena, pulsars, magnetars, plasma interactions, produce broadband noise. They are not known to produce narrowband tones this clean. When the signal drifted in frequency over time, it did so at a rate precisely consistent with the Doppler shift produced by a transmitter sitting on a planet orbiting Proxima Centauri, spinning and moving through space, tugging the frequency up and down as orbital mechanics dictate. The signal appeared when the telescope pointed at Proxima Centauri. It disappeared when the telescope looked away. The standard cosmological model says, and the Breakthrough Listen team itself publicly concluded, that the most probable explanation is radio frequency interference of an unidentified terrestrial or low-orbit origin. Human technology produces signals that can mimic narrowband tones. Satellites, ground-based transmitters, and even internal electronics within the telescope facility itself have contaminated data before. The signal was only detected during one observation window. It was not recovered in follow-up scans. Under the protocols of scientific rigor, a signal that cannot be reproduced is a signal that cannot be confirmed. But the interference explanation carries a burden it has not fully discharged. The Breakthrough Listen pipeline is specifically engineered to reject radio frequency interference. It uses a technique called multi-beam analysis, simultaneously comparing signals across several receiver beams pointed at slightly different regions of sky. Terrestrial interference typically appears in all beams at once. Breakthrough Listen Candidate 1 appeared in the on-source beam. The drift rate was not random. It was orbital. Interference does not usually orbit stars. Some astrophysicists and signal analysts within the search for extraterrestrial intelligence community have noted quietly that if you designed a signal specifically to pass the Breakthrough Listen filter, it would look a great deal like this one. What exactly passed every filter designed to eliminate human noise? If it was interference, why has no terrestrial source been identified in the 4 years since? Why has no peer-reviewed analysis of Breakthrough Listen Candidate 1 appeared in a major journal? If the signal came from a planet orbiting the nearest star to our own, what does it mean that we looked away? And what might be waiting in the data we have not yet examined? The universe, it turns out, may not be broadcasting in the frequencies we expect. Sometimes the most staggering energies arrive not as waves but as particles, singular and inexplicable, carrying more energy than physics says they should be able to hold. The oh my god particle. You are not looking at a telescope feed. You are not watching a screen. You are standing at the edge of Dugway Proving Ground in the Utah desert on the night of October 15th, 1991, and something is about to punch through the atmosphere above your head. You wouldn't see it. That's the thing. The particle itself is invisible, subatomic, smaller than a proton. But when it hits the upper atmosphere at whatever velocity it's traveling, and the velocity is something you will spend years trying to comprehend, it tears through the air like a stone thrown into still water, splitting atoms, generating a cascade of secondary particles, a cone of blue Cherenkov radiation blooming downward through the dark, a shower of daughter particles fanning out across dozens of square kilometers of desert floor. The fly's eye detector at the University of Utah is watching. It catches the light. It measures what arrived. And then the physicists start running the numbers. The fly's eye experiment, operated by a team led by physicist David Bird at the University of Utah, was a ground-based cosmic ray observatory consisting of 67 mirrors arranged to detect the faint fluorescence trails left by ultra-high energy cosmic ray air showers. The instrument had been running since 1981. It had seen things before. It was not easily surprised. On the night of October 15th, the detector recorded a cosmic ray event with a reconstructed energy of 3 × 10 to the 20th electron volts. Written out, 300 million trillion electron volts. The result was published by Bird and colleagues in the Astrophysical Journal in 1995. The event was immediately given a name that the team did not officially sanction, but that the physics community immediately adopted, the oh my god particle. Here's what that energy actually means, physically. The fastest object ever built by human hands, the Helios 2 solar probe, travels at approximately 250,000 kilometers per hour. A baseball moving at the speed of the oh my god particle would carry the kinetic energy of a brick dropped from waist height. Not the energy of a nuclear weapon, not the energy of an explosion, just a brick, dropped, from your hand, to the floor, compressed into a single subatomic particle, into something with no internal structure, into something with a mass roughly equal to 1 proton. The standard cosmological model says there is a hard ceiling on how much energy a cosmic ray can carry across intergalactic distances. It is called the Grayson-Zatsepin-Kuzmin limit, proposed independently in 1966 by Kenneth Grayson at Cornell and by Vadim Kuzmin and Georgy Zatsepin in the Soviet Union. The physics is straightforward. Protons traveling above approximately 5 × 10 to the 19th electron volts will interact with the cosmic microwave background radiation, the cold remnant glow of the Big Bang that fills the entire universe at a temperature of 2.7 Kelvin. Those interactions are inelastic. Energy is lost. Across distances greater than roughly 50 to 100 megaparsecs, approximately 160 to 326 million light-years, no cosmic ray proton should survive with energy above the GZK limit. The universe itself acts as a speed governor. The oh my god particle exceeded that limit by a factor of roughly 6. But the distance problem is only the beginning. The direction of arrival was reconstructed. Right ascension approximately 0 hours, 52 minutes. Declination approximately 48 degrees. The team traced that vector back across the sky. There is no known object in that direction. No active galactic nucleus, no gamma-ray burster, no magnetar within plausible accelerating range, capable of producing a particle at this energy. Some astrophysicists suggest the particle may have been a heavy nucleus rather than a proton, potentially altering the energy calculation. A minority of researchers propose that GZK violation events, like this one, point toward physics beyond the standard model. Lorentz invariance violation, exotic top-down decay processes, or sources of acceleration that current astrophysics has not yet characterized. The telescope array experiment in Utah, successor to the fly's eye, has since detected additional trans-GZK events, none with a clean, confirmed source. What was accelerated to that energy? What structure in the universe is capable of doing that? If the source was within the GZK radius, why is there nothing there? If it came from farther away, how did the particle survive the crossing? And what else arrived that night that the detectors weren't built to see? The desert asks nothing. It just records the light. The next mystery also arrives from outside. Not a particle this time, but an entire object, tumbling through our solar system on a trajectory that the physics of our own neighborhood cannot explain. 1I/Muamua. You are standing at the eyepiece of the Pan-STARRS 1 telescope on Haleakala, Maui, on the 19th of October, 2017, and something is wrong with the object on your screen. Not wrong in the way a calibration error is wrong. Wrong in the way that stops a room. The object is moving, not orbiting, not drifting on the long elliptical arc that every comet, every asteroid, every piece of planetary debris in 4.5 billion years of solar system history has obeyed. It is moving through, passing through the solar system the way a bullet passes through a room, with a trajectory that answers to somewhere else entirely. It entered from the direction of the constellation Lyra. It is already leaving, and it is speeding up. Robert Warwick, a researcher with the University of Hawaii's Institute for Astronomy, was the first to formally identify it in the Pan-STARRS survey data on October 19, 2017, though the object had already made its closest approach to the Sun 18 days earlier, on September 9th, passing within 37.6 million kilometers of the solar surface, well inside the orbit of Mercury. By the time anyone was looking, it was already going. The International Astronomical Union designated it 1I/Oumuamua, borrowing from the Hawaiian for scout or messenger from afar reaching out first. It was the first confirmed macroscopic object in recorded human history to have arrived in our solar system from interstellar space. Its shape, reconstructed from the dramatic variations in its light curve as it rotated, suggested something extraordinary, an object roughly 400 meters in length and between 35 and 55 meters in width, a ratio of approximately 10:1, elongated beyond anything in our asteroid or comet catalogs. As it tumbled, it brightened and dimmed by a factor of 10 every 7 to 8 hours, a light signature that implied either an extreme cigar shape or an equally extreme flat disk geometry, both of which are essentially unknown in naturally formed solar system objects. Researchers Ye Kwanji, Marco Micheli, and Karen Meach, among others, published careful analyses across the astrophysical journal Letters and Nature throughout late 2017 and into 2018, and the deeper they looked, the stranger it became. Here is what breaks the model. As Oumuamua departed the solar system, it accelerated, not slightly, not within the margin of measurement uncertainty, by a factor that exceeded what solar radiation pressure alone, the gentle push of photons from the sun, could produce by approximately 6 times. This is the finding published by Micheli and colleagues in Nature in June 2018, using data from the Hubble Space Telescope, the Canada-France-Hawaii Telescope, and the European Southern Observatory's Very Large Telescope. The acceleration was real. It was measured across multiple independent instruments, and it could not be attributed to gravitational forces from any known body. Objects that accelerate anomalously during solar departure do so because of outgassing, sublimating volatile material, venting jets of gas and ice that act like a rocket thruster. Every comet we have ever observed does this. Oumuamua produced no detectable outgassing, no coma, no tail, no spectroscopic signature of escaping material whatsoever. The standard cosmological model says that small solar system bodies are frequently ejected from forming planetary systems during gravitational scattering events, and that statistically, interstellar space should be full of such objects. This explanation is coherent, well-supported, and entirely reasonable. A dense, desiccated fragment of a shattered exoplanet or exocometary body could theoretically survive interstellar transit and arrive in an unusual shape without producing an observable coma. But the data cannot be made to fit neatly. 6 times the expected radiation pressure, with no outgassing, from an object we saw for 72 days total, that we can never recover, never revisit, never sample. Avi Loeb, chair of Harvard University's Department of Astronomy, published his assessment that a light sail of artificial origin could not be ruled out by the available evidence in Astrophysical Journal Letters in 2018. Most of his colleagues disagreed. The productive tension has never been resolved. What was Oumuamua actually made of? Why did its shape fall so far outside the natural distribution? If it was venting something, why did every instrument fail to detect it? And if it wasn't, if nothing was pushing it, then what was? The universe sends objects through our solar system once every 10 million years or so, by current estimates. This one arrived, accelerated without explanation, and vanished into the dark between the stars. And while we were still arguing about it, something else entirely was humming through the fabric of space itself. The gravitational wave background detected by pulsar timing arrays. You are not looking at the sky, you are listening to it. It is June of 2023. You are inside the data reduction pipeline of the North American Nanohertz Observatory for Gravitational Waves, a collaboration spanning dozens of institutions across the United States and Canada. And the thing that is coming through the instruments is not a sound in any conventional sense. It is a slow, deep, rhythmic warping of space-time itself. Not a pulse, not a burst, a hum that has been there, underneath everything, all along, and you have only just built ears sensitive enough to hear it. The signal is coming from everywhere at once. Here's what makes this impossible. To detect gravitational waves at nanohertz frequencies, waves so long that a single cycle takes between 1 and 10 years to complete, you cannot build a detector. The detector you need is the galaxy. The North American Nanohertz Observatory for Gravitational Waves collaboration, along with 4 independent international teams, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, the Indian Pulsar Timing Array, and the Chinese Pulsar Timing Array, operating together under the International Pulsar Timing Array Consortium, used millisecond pulsars as reference clocks. These are collapsed stellar remnants spinning hundreds of times per second with a rotational stability that rivals atomic clocks. When a gravitational wave passes through the galaxy, it stretches and compresses the fabric of spacetime between Earth and each pulsar by a fraction so small it staggers comprehension. We are talking about timing deviations measured in nanoseconds, across baselines measured in thousands of light years. Across 15 years of data, across 67 pulsars, across 5 independent collaborations on 4 continents, using 4 separate radio telescope arrays. The signal appeared in all of them. The 5 simultaneous publications landed in journals, including the Astrophysical Journal Letters and Astronomy and Astrophysics in June of 2023. The signal bore the precise statistical fingerprint predicted for a stochastic gravitational wave background, specifically a correlation pattern between pulsar pairs known as the Hellings-Downs curve, named for the 1983 theoretical prediction by Ronald Hellings and George Downs. The detection of this curve across independent datasets was not a statistical fluke. The confidence levels reached 4 sigma in the North American Nanohertz Observatory for gravitational waves data alone. The hum is real. Space-time itself is vibrating at frequencies the human nervous system cannot perceive, and has been for as long as human civilization has existed, and longer. The standard cosmological model says this is the accumulated gravitational wave output of supermassive black hole binaries, pairs of black holes, each massing between 100 million and 10 billion solar masses, locked in orbits so slow that a single revolution takes thousands of years, spiraling together across cosmic time as they release energy in waves long enough to dwarf entire solar systems. The universe contains hundreds of millions of galaxies. Galaxies merge. When they merge, their central supermassive black holes eventually find each other. The integrated signal from all those mergers, all across the observable universe, should produce exactly this kind of background hum. It is one of the most confident predictions in gravitational wave astrophysics. But the data doesn't support this cleanly. The signal is too loud, by a factor of several. The measured amplitude of the gravitational wave background is significantly higher than what the population of known supermassive black hole mergers should be able to produce, even under generous assumptions about merger rates and black hole masses. Some astrophysicists suggest that the excess power could indicate a previously unknown population of supermassive black hole binaries, far more numerous or more massive than optical surveys have revealed. A minority of researchers propose more unsettling alternatives: cosmic strings, topological defects left over from phase transitions in the early universe, threading spacetime with tensions so extreme that their vibrations alone could account for the signal. Others have raised the possibility that the background contains contributions from processes that occurred in the first seconds after the Big Bang itself, primordial gravitational waves, encoded in the structure of spacetime before a single star had formed. 5 independent teams, 4 continents, 1 signal. and it is louder than it should be. Where is the energy coming from? Is the census of supermassive black hole mergers catastrophically incomplete? Could a network of cosmic strings be woven through the large-scale structure of the universe, invisible to every instrument we have built except this one? Is space-time itself trying to tell us something about the first moments of existence that our models have no framework to receive? The universe hums at frequencies no human ear will ever hear, and the next signal in this record was caught not by a planet-spanning array of pulsars, but by a single, baffled radio telescope operator staring at a signal that appeared to come from a direction where nothing should be. SHGB 02 plus 14A. You're not at a telescope. You're at a screen. It's 2003, and you're one of 5 million people who have downloaded the SETI at Home software, the distributed computing project run by the University of California, Berkeley, that borrowed idle processing power from personal computers around the world to sift through radio telescope data for patterns that might mean something. Your machine does the math while you sleep. You never expect to find anything. Nobody really does. The project has been running since 1999, and the silence has been total and unremarkable. Then a signal gets flagged. Not by your machine, not by any single machine. By the accumulated attention of a distributed network of millions of processors, all of them arriving at the same small, strange conclusion about a narrow slice of sky that contains, as far as anyone can determine, absolutely nothing. The signal is designated SHGB 02 plus 14A. The Arecibo Observatory in Puerto Rico, at the time the largest single-aperture radio telescope on Earth, a 305-meter dish carved into a natural limestone sinkhole, detected it 3 separate times. The first detection came in March of 2003. The second in August of 2003, the third shortly after. Each detection came from the same region of sky, right ascension 2 hours 26 minutes 31 seconds, declination plus 14 degrees 29 minutes 18 seconds. Each time, the signal appeared at 2.462 gigahertz, drifting slightly, shifting at approximately 1.15 hertz per second, which would be consistent with an object either accelerating or located on a rotating body. Here's what makes this immediately strange. That frequency, 2.462 gigahertz, sits at approximately 1,666 times the frequency of neutral hydrogen, the 21-centimeter line that SETI researchers have long considered a universal cosmic landmark, a frequency any technologically sophisticated civilization might recognize as meaningful. The signal is narrowband, which in radio astronomy terms means it occupies an unusually thin slice of the electromagnetic spectrum. Natural astrophysical processes, pulsars, quasars, gas clouds, stellar coronae, tend to produce broadband emissions spread across wide frequency ranges. Narrowband signals are the kind that transmitters make. The region of sky from which SHGB 02 plus 14A originated contains no catalog star within 1,000 light-years. Not a dim one, not a distant one. Nothing in any stellar catalog that might anchor the signal to a known physical source. The signal was reported by researchers including Dan Wertheimer, chief scientist of the SETI at Home project, and documented in the July 2004 issue of New Scientist by journalist Michael Brooks. It received brief but significant public attention before the scientific community largely moved past it. The standard cosmological model says that unexplained narrowband radio signals detected from direction-consistent sky positions almost certainly have terrestrial or near-terrestrial origins. Radio frequency interference from satellites, aircraft, ground-based transmitters, and even the observatory's own instrumentation can mimic the characteristics of an astronomical signal with surprising fidelity. The frequency drift observed in SHGB 02 plus 14A, 1.15 Hz per second, is within the range that equipment artifacts or ionospheric effects might plausibly produce. But there are things this explanation strains to fully account for. The signal appeared 3 times from the same precise coordinates across a span of months. Direction-consistent repetition is not a hallmark of terrestrial interference, which tends to be transient and positionally inconsistent. The signal was also, by all measured parameters, genuinely faint, too faint, some researchers noted, to have originated from a transmitter anywhere within the solar system at a detectable power level. And the region of sky it points to remains, to this day, empty of any confirmed natural source that could produce it. The SETI at Home project officially ended active data collection in 2020. SHGB02 plus 14A was never officially explained. It was never officially classified. It sits in the literature as an unresolved data point, flagged, documented, and then quietly filed into the growing archive of things the universe has said that we do not know how to answer. Where is the source? Why that frequency in that harmonic relationship to hydrogen? Why 3 detections, months apart, from an empty coordinate in a direction that leads to nothing we have ever named? And if this is interference, where is the interfering object? Perhaps the universe was not trying to reach us. Perhaps it simply left something running, in a direction we happen to be listening, from a place we cannot find. The sky above Arecibo held its silence. But somewhere far stranger, something else would not wait. It would repeat, with a rhythm almost too precise to be an accident. FRB 1800916. J0158 plus 65. You're watching a clock. That's what it feels like. You're at the Canadian Hydrogen Intensity Mapping Experiment, CHIME, the massive cylindrical radio telescope sprawled across the mountains of British Columbia, and you've been watching this particular patch of sky for months. The source is 500 million light-years away, embedded in a spiral galaxy, catalogued as SDSS J015800.28 plus 654253.0, and every 16.35 days it does the same thing. It wakes up, it screams, then it goes silent for 12 days, then it screams again. Every time, without deviation, without drift, with a mechanical, almost deliberate precision that no natural process in our current models can cleanly produce. You've stopped calling it an anomaly. You've started calling it a schedule. The signal itself was first captured in 2018 by the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope unlike any other in operation, designed not as a traditional steerable dish, but as a fixed cylindrical reflector stretching 100 meters in width, scanning the sky as Earth rotates beneath it. The instrument was built primarily to study dark energy through hydrogen mapping, but its extraordinary sensitivity to fast radio bursts turned it into the premier detection instrument for one of astrophysics' most confounding phenomena. FRB 180916 was logged during the telescope's commissioning phase and initially appeared to be a standard fast radio burst, a millisecond duration pulse of radio energy so intense it briefly outshines every radio source in the visible universe combined. Then the team, led by researchers at the Dominion Radio Astrophysical Observatory and the University of British Columbia, began collating months of data. The pattern emerged with a clarity that stopped people mid-sentence in collaboration meetings. Published in the journal Nature in February 2020, the analysis confirmed it. The burst repeats on a cycle of 16.35 days, active for approximately 4 days, silent for approximately 12, then active again, then silent again. The timing precision is extraordinary. The period holds across observations spanning hundreds of cycles without measurable drift. The standard cosmological model says that periodic signals from cosmic sources arise from geometry and motion. A pulsar rotates, and its beam sweeps across our line of sight with each revolution. A binary star system occults its companion on a fixed orbital schedule. A precessing neutron star wobbles its emission cone in and out of our view at a rate set by its spin-orbit coupling. These are the mechanisms science reaches for when something repeats on a clock. They are elegant, they are tested. They are extraordinarily well understood. Applied to FRB 180916. However, they break. The most favored mainstream proposal involves a binary system, a neutron star orbiting a massive stellar companion, possibly a B-type star surrounded by a dense plasma disk. As the neutron star swings toward us through its orbit, its bursts reach us unimpeded. As it swings behind the companion's disk, the plasma absorbs and scatters the signal into silence. The orbital period of 16.35 days is not implausible for such a system. But detailed modeling has repeatedly failed to find a binary configuration that produces the observed active window duration, the abrupt transitions between states, and the subburst structure simultaneously. The fit is always partial. Something is always left over. Some astrophysicists suggest the periodicity arises from free precession, a neutron star wobbling on its own axis, sweeping its beam across our sky on a cycle set by its internal structure rather than any companion body. A minority of researchers have proposed that the source is not a neutron star at all, but something more exotic, a magnetar embedded in a dense circumsource environment whose geometry modulates the burst visibility in ways not yet parametrized by any published model. None of these proposals have been ruled out. None of them fully work. And that is perhaps the most unsettling thing about FRB 180916. It's not the signal that disturbs, it's the schedule. 16.35 days, not approximately, not roughly, exactly. A pulse from 500 million light-years away, arriving on time, every time, like a transmission waiting to be acknowledged. What natural mechanism runs this precisely across 500 million light-years of intervening space, gas, and time? Why does the active window end so abruptly, rather than fading as an orbital or precessional geometry would predict? Why does this source repeat when the overwhelming majority of fast radio bursts detected to date do not? And if this is a clock, what is it counting toward? The hydrogen atom has its own signal embedded in the fabric of the cosmos, and what researchers found hiding inside its spectral line may be no less difficult to explain. The anomalous 21-centimeter signal fluctuations. You are standing at the edge of time itself. Not metaphorically. The signal you are analyzing was imprinted on the universe when it was 180 million years old. The cosmos had just emerged from its dark ages, that vast, lightless era before the first stars ignited, when hydrogen gas filled everything, when there was nothing to see and nothing to see it with. And from that primordial darkness, the experiment to detect the global epoch of reionization signature has pulled something out that should not be there. A dip, a trough in the radio spectrum, an absorption feature so deep that the physicists running the experiment in the Western Australian desert initially assumed their instrument was broken. It wasn't broken. The experiment to detect the global epoch of reionization signature, operated by a team led by Judd Bowman at Arizona State University and deployed at the Murchison Radio Astronomy Observatory in Western Australia, announced its results in February of 2018 in a paper published in the journal Nature. The instrument is a single antenna, roughly the size of a dining table, designed with extraordinary simplicity to detect one of the faintest signals in the known universe, the absorption of cosmic background radiation by neutral hydrogen gas at a frequency of 1,420 MHz, the famous 21-centimeter line, redshifted by cosmic expansion into the range of roughly 78 MHz by the time it reaches us, across the span of 13.5 billion years. The 21-centimeter line is the universe's own fingerprint. Neutral hydrogen absorbs radiation at this precise frequency due to the quantum mechanical spin flip of the electron in a hydrogen atom, a transition so fundamental, so universal, that it has long been considered the most reliable cosmological probe available to radio astronomy. When the first stars began forming and flooding their surroundings with ultraviolet radiation, they coupled that radiation to the hydrogen gas, causing the gas to absorb the cosmic microwave background. That absorption should produce a detectable trough in the radio spectrum, a global signal that the experiment to detect the global epoch of reionization signature was specifically built to find. They found it. At a central frequency of 78 MHz, corresponding to a redshift of approximately 17, the trough appeared precisely where the models predicted it should. The epoch was right. The shape was right. The depth was not. The standard cosmological model says the temperature of the hydrogen gas at that epoch, some 180 million years after the Big Bang, should have been cooling from the hot plasma state of the early universe, but still far warmer than the cosmic microwave background itself. The absorption signal that results should be no deeper than approximately 0.2 Kelvin against the background radiation temperature of roughly 46 Kelvin at that redshift. This is the hard physical ceiling. The gas cannot absorb more than the thermodynamic difference allows. The standard model is not ambiguous on this point. The signal Bowman's team detected was roughly 0.5 Kelvin deep, more than twice the maximum permitted depth. In one measurement, a simple antenna sitting in the Australian desert had returned a number that the entire edifice of standard cosmological physics cannot accommodate. Here's what makes this impossible. For the trough to be that deep, either the hydrogen gas was significantly colder than any known process can explain, or the radiation background it was absorbing against was significantly hotter than the cosmic microwave background alone would predict. Both possibilities require physics that does not currently exist in any confirmed theoretical framework. But the data doesn't support this being a measurement error. The team spent years testing for systematic instrumental effects. Independent researchers scrutinized the analysis. A competing experiment, the shaped antenna measurement of the background radio spectrum, or SARAS-3, published results in 2022 that introduced some tension with the original detection, though the underlying anomaly in the signal depth has never been satisfactorily resolved. Some astrophysicists suggest the answer lies with dark matter. A specific class of models proposes that if dark matter particles interact weakly with ordinary baryonic matter, they could have acted as a refrigerant, draining thermal energy from the hydrogen gas in that early epoch, cooling it below the floor the standard model enforces. Others propose an exotic radio background generated by early universe processes we have not yet identified, heating the radiation field rather than cooling the gas. Both explanations invoke invisible physics. Neither has been confirmed. And the universe was already 180 million years old when it sent this signal, already ancient by some measures, and already keeping secrets. What was cooling the gas in the dark before the first stars existed? What unknown background radiation filled that primordial void? If the standard model's thermal ceiling has been breached, what else about that epoch is wrong? And if dark matter can refrigerate hydrogen on a cosmic scale, what else is it doing that we cannot see? Something stranger waits even closer to home, at the very center of our own galaxy, where a radio source blinks into existence and vanishes on a schedule that defies every known category of astrophysical object. GCRT J1745-3009. You are watching a clock that shouldn't exist. It's November 2004. You're sitting inside the Very Large Array Control Facility in Socorro, New Mexico, surrounded by the low hum of processing equipment and the soft fluorescent light that makes every late shift feel like the middle of the night, regardless of what the sky is doing outside. The data rolling in from the 27-dish antennas, stretched across the New Mexico desert, has been routine for hours. Galactic center observations, background noise mapping, the slow cataloging of a region so dense with radio sources that distinguishing signal from interference is more art than science. Then something pulses. Strong, clean, unmistakable. A radio burst from the direction of the galactic center, bright enough to sit well above the noise floor, arriving at a frequency near 1030 megahertz. You note the time and wait, and then, exactly 77 minutes later, it pulses again. You wait again, telling yourself this is coincidence, that the galactic center is a chaotic, violent place, filled with supernovae and magnetars, and the gravitational shredding of infalling matter, that patterns appear in noise if you stare long enough. 77 minutes later, it pulses again. It is not coincidence. The detection was made during a survey of the galactic center region conducted by Scott Hyman of Sweetbriar College and colleagues using archival Very Large Array data. The results were published in the journal Nature in September 2005. What Hyman's team found when they processed the archival observations from September 2002 was a radio transient unlike anything cataloged before. 5 discrete bursts arriving from the coordinates GCRT J1745-3009, located in the direction of the galactic center, approximately 25,000 light-years from Earth. Each burst lasting approximately 10 minutes, each burst separated from the last by exactly 77 minutes, each burst emitting at a peak flux density of approximately 2 Janskis, making it, briefly, the brightest transient radio source in the entire sky, below a frequency of 1000 megahertz. And then it vanished. Between the 5 observed bursts in 2002, nothing. In subsequent follow-up observations, nothing. A faint, possible detection in 2003 that hinted at recurrence, but nothing confirmable. Whatever this object is, it turned on, repeated itself with mechanical precision 5 times, and disappeared. Here's what makes this impossible. The 77-minute periodicity is not consistent with known astrophysical emission mechanisms at this timescale and frequency. Pulsars repeat on timescales of milliseconds to seconds. Rotating radio transients operate on similar intervals. X-ray binaries produce periodic outbursts, but their cycles are driven by orbital dynamics and accretion physics that produce irregular duty cycles and variable burst profiles. GCRT J1745 minus 3009 emitted bursts of nearly identical duration and flux across 5 complete cycles. That regularity, that mechanical, clock-like periodicity at 77 minutes, has no confirmed physical home in the current taxonomy of astrophysical objects. The standard cosmological model offers several candidate explanations, all of them reasonable, all of them incomplete. The source may be a highly magnetized neutron star, a magnetar, undergoing periodic emission driven by some resonance between its rotation and magnetic field dynamics. It may represent an ultra-long period pulsar, a class of object only recently confirmed to exist, whose rotation period of 77 minutes would place it far beyond the pulsar death line, where emission should theoretically cease. It may involve a binary system in which one compact object eclipses or interacts with another on a precise orbital period, producing the observed burst cadence. But none of these explanations fully account for the data. The burst morphology, the specific shape, duration, and spectral properties of each pulse, does not cleanly match any of the proposed emission models. The source's location near the galactic center places it in a region of extraordinary magnetic field complexity and interstellar scattering, which makes precise characterization enormously difficult, and its disappearance remains unexplained. Known periodic emitters do not simply stop. What turned on at the galactic center in 2002? Why 77 minutes, a period that appears in no known natural resonance frequency of any confirmed compact object class? Why 5 bursts, and then silence? If this is a pulsar rotating once every 77 minutes, how is it still emitting at all? And why, when we pointed every available instrument back at those coordinates, did the sky give us nothing? The galactic center holds its secrets tightly, but deep in the old stellar suburbs of a galaxy beyond our own, something else was transmitting, and what made it strange was not what it was doing, but where it was doing it from. The fast radio burst source in globular cluster M81. You are listening, not watching, not analyzing. Listening, the way radio astronomers actually work, translating the universe's electromagnetic breath into numbers, into plots, into the slow accumulation of data that occasionally, without warning, becomes something that rewrites everything you thought you understood. It is January of 2022. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has flagged a repeating signal, Fast Radio Burst Designation FRB 212249A. The signal has been arriving for months, intermittent and precise, each burst lasting less than a millisecond, each one releasing in that fraction of time more energy than the sun produces in 3 days. Your localization software narrows the origin. Galaxy Messier 81, 11.8 million light-years away, close enough, on cosmological scales, to be considered practically a neighbor. And then the software narrows further, and the room gets very quiet. The signal is not coming from the star-forming disk of Messier 81. It is not coming from any region of active stellar birth, any field of young massive stars, any zone where the universe is still building the kinds of objects astronomers believe produce fast radio bursts. It is coming from a globular cluster, a dense, ancient, gravitationally bound sphere of several 100,000 stars, stars so old that the youngest among them formed roughly 10 billion years ago, in the early chapters of cosmic history, before our solar system existed, before Earth had any right to exist, before the atoms in your body had been forged by anything. Here is what that means. The dominant theoretical framework for fast radio bursts, the one supported by the majority of observational evidence, centers on magnetars, highly magnetized neutron stars formed when massive stars, stars many times heavier than the sun, exhaust their fuel and collapse catastrophically. The collapse is violent and fast and extraordinary. It leaves behind an object roughly 20 kilometers across, containing more mass than the sun, spinning dozens of times per second, wrapped in a magnetic field so intense it would strip the iron from your blood at the distance of halfway to the moon. Magnetars are young objects. They require young, massive stars. They require an environment actively producing new stars, which means regions with the gas and dust and density conditions to form stars in the first place. Globular clusters have none of this. They are cosmological relics. They stopped forming stars billions of years ago. Their massive stars burned hot and fast and died long before Earth formed. What remains is a tightly packed community of low-mass, ancient stellar survivors, red giants, white dwarfs, neutron stars left over from a younger epoch, and the gravitational dynamics that occur when you pack several 100,000 objects into a sphere only roughly 100 light-years across. There are no young, massive stars in M81's globular cluster. There is no mechanism, under the standard theoretical framework, to produce a magnetar there today. And yet the repeating burst arrives. Millisecond flash. 3 days of solar energy. 11.8 million light-years. Again and again. The standard cosmological model says this is still consistent with a magnetar origin, specifically that ancient neutron stars in globular clusters can be recycled through binary interaction, accreting material from a companion star, possibly spinning up and intensifying their magnetic fields through dynamics unique to the crowded stellar environments of globular clusters. The paper formalizing the localization, published in Nature in 2022, and led by researcher Franz Kirsten, of Chalmers University of Technology, acknowledges this pathway and takes it seriously. The environment is unusual, but the object producing the burst may not be. But the crowded stellar environment explanation introduces its own complications. Globular clusters are factories for exotic binary systems, millisecond pulsars, accreting white dwarfs, low-mass X-ray binaries. Some researchers now ask whether fast radio bursts might emerge from mechanisms entirely unrelated to magnetars, from interactions between compact objects, from processes that don't require youth at all, only proximity, gravity, and the right kind of violence between very old things. Which means we may not understand what makes a fast radio burst at all. What else are we looking for in the wrong kind of place? What other signals have we dismissed because the source environment made no sense? If ancient stellar graveyards can produce what only violent stellar birth was supposed to produce, what does that tell us about the rules we have been using to read the universe? And what if those rules are not wrong exactly, but simply incomplete in ways we haven't yet found the language to describe? 10 signals, 10 silences where an explanation should be, and somewhere in the distance between them, the question the universe has been asking all along. What strikes you when you lay all 10 of these signals side by side is not any single impossibility. It is the pattern of impossibility, a 72-second burst from the direction of Sagittarius, carrying more information than noise should carry. A signal from the nearest star to our sun, arriving on the precise frequency hydrogen uses to speak across the void. A particle hitting our atmosphere with the kinetic energy of a thrown baseball, launched from somewhere the laws of physics say nothing should be launching particles. An interstellar object tumbling through our solar system on a trajectory that doesn't quite add up, accelerating in ways that rock and ice alone cannot explain. A gravitational wave background humming beneath the fabric of space-time itself. A chorus so vast that dozens of dead stars had to be listening for years before we even heard it. The pattern is this. We keep building models, and the universe keeps sending signals that arrive just outside the boundaries of those models. Not far outside. Just enough outside. As if the cosmos is not indifferent to being understood, but is simply too large, too old, and too strange to be contained by the frameworks of a species that has been pointing instruments at the sky for roughly 100 years. What none of our current physics can fully account for, not the standard model of particle physics, not lambda CDM cosmology, not general relativity at every scale, is why these anomalies cluster the way they do. Why the repeating fast radio bursts pulse on a 16.35-day cycle, as regular as a heartbeat. Why the galactic center produces transient radio sources that appear, broadcast in a structured pattern, and vanish. Why globular clusters, ancient, dense, by every standard model account the last place you would expect a coherent fast radio burst, produce them anyway. Each anomaly, in isolation, can be rationalized. A known pulsar, perhaps. An unusual magnetar, an instrumental artifact that wasn't quite an artifact, but together, these 10 signals form something harder to dismiss, a sustained argument, written across billions of light years and billions of years, that the universe contains structures and processes and perhaps even architectures that we have not yet named. We did not build our telescopes to find things we cannot explain. We built them to confirm what we already suspected. And yet here, at the edge of detection, at the threshold of what our instruments can barely hear, something keeps transmitting. We do not know what it is. We do not know if it is one thing, or many things, or a property of the cosmos itself that we lack the mathematics to describe. We only know that the signals keep arriving, that the data keeps breaking the models, that the universe, 3 years or 30 years or 3 billion years from now, will still be sending information across distances that make the whole of human history look like a single frame of static, and that somewhere in that static, something is waiting to be understood.